Thank you so much for coming along. I hope you find this talk interesting. I actually gave my first public talk at NDC TechTown last year, and so I was really, really pleased to get the email to be invited back. So I hope you enjoy what I'm going to talk about. This is just a kind of taster of what's coming later. So this is the thing called the Bloomberg Terminal, which is basically a trader workstation that's all over the trading floors of the world. And this is a real-time analysis of the UI thread that this is actually running right now. And we're going to talk about what this means and how we get there and how we actually make a system that runs reasonably fast. This also gives you a scale of the data that's coming in. You know, these are news story headlines that are being generated in real time right now. So this isn't like Twitter. You know, behind each one of these there is a story, which may have media, it may have pictures, it may have deep analysis, but this is how they're coming in from all over the world, and this is just mostly human-generated news. There's also actual real-time financial data, which is orders of magnitude more than that, but it just gives you a sense of the fact this is a very dynamic kind of place for data. Anyway, coming back to that later on. Okay, so going away. Right, okay. So as I say, welcome. I'm Paul Williams. I work at Bloomberg in London mainly, and this is a talk about how we design a desktop platform for near real-time financial data and how we go about measuring how this thing is actually behaving. So the agenda is really talking about this terminal, talking about one of the core systems embedded into this terminal called data layer, which is a layer that processes data. We're not so good at names for things. I'm also going to talk about embedding Chromium. Pretty much all of our GUI is rendered using open source Chromium embedded browser core. And I'm going to talk about what that means in our world. I'm going to talk about instrumentation, the kind of principles we use to measure how things are behaving, how we actually assess slowness. If a user says, this feels slow, what does that actually mean? How we record and playback what's going on so we can actually generate reproducible test cases. And also some of our current research we're doing into WebAssembly. I know that really one of the first times I heard about WebAssembly was actually at this conference last year when Adi Shavit was talking about cross-platform development, and he gave a great talk, including how you can actually incorporate C++ into a browser platform. And it's something that we've been looking at very, very intently and has produced some very interesting and intriguing results so far. So who am I? Very quickly, I wore white trousers in the 80s. I learned most of my kind of how computers work from actually programming very early sort of music sequences for live use in the university bar. I did some work in the games industry. I then spent 9 years doing kind of a traditional full stack, which was basically from the firmware, up through drivers, operating systems, porting compilers on custom parallel processing hardware. Who remembers the i860? Probably nobody in this room. It was at the time it was the fastest floating point processor. I've been involved in actually setting up teams in some of our other offices around the world. This is our San Francisco meetup space that we have. And the last 20 years, I've been working at Bloomberg, primarily involved in the desktop side, actually, which is very much the world of high-performance C++, and nowadays integration with JavaScript as a scripting environment within the same processes. And I'm a manager developer. I still like to think of myself as a developer, mentor in our offices, and I'm very, very passionate about seeing the next generation do this stuff and more, and improving diversity and actually seeing us be more kind in this industry, which I see a lot happening, particularly at conferences like this. It's really, really wonderful to see. So first stage, Bloomberg Terminal, what is it? It's if you ask one of our product or salespeople, it's a financial and business data analytics portal connecting the most influential people in this field. What makes it interesting is that it's near real time. It's not just static financial reports and so on. Multi-window, multi-screen. Some traders have 8 HD or 4K monitors, a lot of pixels to update. Built using hybrid desktop technologies, a lot of C++, a lot of integration with JavaScript, a lot of JavaScript code actually, and embedding Chromium. And the way we think of it is a cluster of 300,000 desktop computers that we can't see, we can't touch, but we really care about. We really care about how they behave. And they're not only running our software, they're running other people's software as well. So we have to be really good citizens at the desktop. It's not like programming an Xbox or a PlayStation where you can kind of take over the machine and nobody else cares when you're running your game. Users expect it to be fast and reliable. It's not cheap. It's a high-quality service. So what's going on inside? On our server side, which I'm not really going to talk about, I'm just going to touch on it here. We have, obviously, application engines that run a lot of our business logic. We have continuously running data services. You know, some data is actually processed overnight to be ready for the next day. And at one point, we actually were using GPU farms to do some of this work because if we, for example, ran a Monte Carlo simulation using traditional hardware, it wouldn't finish on time. We just couldn't scale it. So we actually found that, you know, GPU for mortgage calculations kind of sounds a little bit odd, but actually it really helps us. And then we have a real-time database, which we call the ticker plant, which is the thing that is feeding out real-time updates. You know, it can be up to 100 billion updates a day, sometimes 10 million updates in the first second of one of the New York exchanges actually opening. We have a kind of network to actually deliver this data out to our clients around the world, and then we have these terminals running in this kind of environment. This is the New York Stock Exchange, for example. Many banks and so on have these terminals. So it's a pretty simple architecture with a few little interesting details. So if we think of a typical in-panel function, people like the keyboard in our world very much. You know, somebody will run what's called an in-panel function. There will be data coming from our servers to populate this screen, and then it will open a subscription that will then feed real-time data in a push fashion down to the desktop. And then much of the interaction will go on purely on the client side while real-time data is still flowing. And then, so we try and limit our server interactions as much as we can. But obviously, when you try and do something new, you're going to have to go back to our servers on the back end. Looking inside this, what's actually going on there? Traditionally, and this is where I did a lot of my own development through the years, was actually a fully, purely homegrown UI stack written in C++, which served us well for quite a lot of years. But it kind of, every time you've got to roll out new software to actually change anything, it's not so great. So we actually got some PlayStation developers on the team, and they brought this little thing called Lua, very, very lightweight scripting engine, which was our first foray into actually doing scripting within the desktop product, within the infrastructure layer. And again, that served us quite well, but it was fast but relatively inflexible because everything was, the look and feel was purely coded in C++ for a long time. More recently, we've come up with a much more flexible, scalable model where we have multiple processes to start with, running distinct applications, much more geared to modern hardware where you've got multiple cores in a machine, and we've got a far more flexible render subsystem. It kind of looks the same, but that's intentional. We now have the capability to make it look like anything. But for many of our users, they basically want it to look like it looked 30 years ago. With more powerful analytics and much wider breadth of data. But many users still kind of like to use it in the way they have been using it before. So if we dive a little bit deeper, what do we find inside one of these application container processes? There's obviously a management layer going on. Data subscription, as you might imagine. There's going to be this thing called data layer, which I'm going to dive into in a moment. An application engine, and then beneath that, kind of underpinning all of this, we have the embedded Chromium subsystem, which comprises the browser core and the V8 JavaScript engine. Beneath all this, which is really very much where my technology passion is the metrics subsystem. So thinking about how this whole thing fits together, and people often ask why don't you just use the web for this? Surely the web nowadays is good enough. The web is still primarily request response. All the asynchronous AJAX related stuff is obviously surprised us all initially and then became incredibly popular. It still currently doesn't beat, being able to push real-time data at the same time as handling a kind of request-response service. And we're finding, for some of our data processing, we're not quite at the stage where a browser is fast and efficient enough for us. A typical Bloomberg user experience might involve, 10 to 50,000 updates per second across, 100 or sometimes 200 top-level windows on the desktop. Primarily 2D grids and charts. So, good GPU accelerators don't really help us that much. Lots of flowing text, complex visualizations in some cases, but with live data. And it's common to have, orders of magnitude more rows off screen than you can actually see. I might have 100,000 trade orders in my blotter, but I only want to see the 20 that are most relevant to me right this second. So there is a need for a high-performance native processing layer alongside the UI, which is what we're going to talk about next. So data layer. Kind of fits in here in the scheme of things. What is it? It's a fully programmable, fully implemented in C++, near real-time streaming data transformation engine, integrated with the other components, and with Chromium via the V8 JavaScript engine. Much like a browser, if you were a traditional web developer, you might want to hook up to IndexedDB or local storage services, which are implemented natively in the browser, but are things that you can actually access from your JavaScript. The DataScript subscription module brings in the pushed real-time data into this world based on programmable rules that can be set by our application teams. So inside this data layer component, this is really just a set of building blocks that an application developer can piece together to form this streaming pipeline. So we have a thing called Worksheet, which is analogous to Excel, basically. If you're, you can express Excel-like expressions primarily, per column rather than in individual cells, or you can actually do it any way you like. And it also supports hooking up to the subscription layer. We have, obviously, components that can do things like filtering, sorting, based on what can be quite complex criteria. And a component called the data source, which is really an engine that, using templates, can transform numerical and string data into the formats you actually want to see on the screen, with all the sort of formatting rules that you might want to apply to actually get the data into the GUI. So this thing, you tend to set it up as a rules-based system and let it run for your particular application use case. You can do more with it. So, for example, you can combine data together. You might have streaming data coming through your worksheet combined with some reference data in another table that you want to show together within a particular piece of the GUI, or you might want to split it. So, the same data pipeline might be driving something like a trading blotter and a trading ticket and maybe some kind of chart. So you can hook these things together in any way that makes sense. You can build trees. We have something called aggregation view, which transforms this data into trees with partial sums and averages at each node and so on. Row history view, for example, if you've got streaming news headlines coming in, you might want to turn that into a sort of 2D representation as each headline comes in, so you can actually display that in some kind of scrolling GUI with history rollback and so on. To actually program and understand this pipeline, we have a thing called DataNow Inspector, which is actually written in JavaScript and allows you to understand what's going on inside this pipeline. And you think, this looks kind of crazy for this kind of display. But there's going to be lots of rules embedded here which allow this display to handle all the nuances of different kinds of trades that may happen, that will allow me to maybe drill down into this system and do interesting things without having to go back to the server. There's going to be a lot of state held in this system, specifically for this kind of application. How do we make it fast? And how do we make it run efficiently in a small footprint? There's a few things. We have something called Datum, which I'm going to talk about for a moment. We make use of polymorphic allocators. Now, of course, I'm from Bloomberg. I have to mention allocators. Sorry about that. But it's something that really helps us. And now that they are, there's this new polymorphic allocator in the standard in C++ 17. It's something that we really feel it's we really want to show the world how we've used them, because it's actually very easy, and for us it really, really helps us. And some of the optimization tricks we actually use within the data layer infrastructure to minimize CPU usage. So, why might we want our own custom data types within each grid cell? Because we have grids like this. Now, something like this is we call it a worksheet component. A user might have 20, 30 of these on the screen at the same time. Probably not sorted by time, because that's fairly useless, but I thought I'd give you an idea of the data. What you can't really see here is there's probably, there's going to be tens of thousands of rows of this data, and maybe hundreds of columns, because a lot of the nuances of how this data needs to be displayed and the rules for processing it is often done in off-screen equations. So the numbers add up. So if I've got, for example, maybe a worst case, 100,000 rows of data with 300 columns, even if each cell is only represented by one double, and it's going to be more than that usually, because there's going to be other data associated with each cell, that would be 240 megabytes of data. And if our data type for a cell doubled in size, that's another 240 megabytes. So it matters. It matters, paying attention to the detail at this level. So what is Datum? Datum is a compact, bitwise copyable variant type. A trivial, unoptimized implementation would look something like this, where there's a union of all the different things it can be, and something that allows you to select which of those it currently is. The problem is that there's quite a lot of waste in here, partly through having that extra union type field, partly through alignment issues typically. So for example, this is holding a double, then even if type is only a few bits, this thing is probably going to end up being 16 bytes in this kind of implementation because of alignment. So that's, as we've just shown, that's not ideal. So can we do better? Now, ideally, we'd want to do something like this. Is there any way we can actually overlay the type somehow into the data? And you think, well, that's not going to work, because you're going to be trashing our actual data by putting the type in there. However, if you look at all these data types, particularly on a 32-bit platform, only double uses the whole thing, if the whole 8 bytes. So all the rest actually have a few bits spare in them. Pointers obviously would only be 32-bit in this particular example. The others, generally, you can keep smaller than the full 8 bytes. So is there anything we can do here? Well, who remembers IEEE floating point format from their days at school or college? Or right. So I kind of had to refresh myself on this as well. One of the interesting things about this, I'm sure you'll remember, you have the significand, which is sort of the numeric part, and then really the kind of scale factor. It's the exponent, where this is actually in reality, and the sign on the end. Just so happens there's a whole range within the possible bit patterns here, which represent the signaling nan value. So if you get a nan, which means not a number, it's the excuse. Why isn't this a number? What's the reason for this not being a number? But in many real-world scenarios, you don't really need to know that the reason I've got not a number. You just need to know it's not a number, because probably you're going to display blank or error or something like that. So if we sacrifice all the distinct nan values except one, which we use to represent generic and not a number, we can actually use these bit patterns, or some of them, for our type, if we're careful. And it's kind of a little bit knotty code, but it does work. So we can effectively remove a separate field from this union and kind of overlay these distinct types into these spare values within inside double. You might all be feeling this is disgusting. It actually, obviously, if you surround this by a serious set of unit tests and you really test everything out of it, you can be pretty sure this is going to work, and that's exactly what we do. It's a little bit more tricky because you kind of have to move everything else around so that things like the pointer kind of aligns correctly so it doesn't actually trash those bits and so on. But you can make it work, and not only that, you can even end up use it as a short string optimization. If you've got strings which are only up to 6 bytes, you can actually accommodate those in line. And actually, we find in reality there are a lot of strings in the world that are pretty short. So you can actually keep this as a very, very lightweight, bitwise, copyable, small data structure that kind of does most of the things a variant can do. One of our colleague engineers from New York actually gave a talk at CPPCon last year, which is here. I'm happy to send round links to anybody who's interested afterwards. So another thing we do is we make use of PMR, polymorphic allocators. So for those that don't know about this thing yet, we all know C++ is typical C++ memory use is very dynamic. You know, the language supports incredibly powerful, complex data structures, which need to grow in all kinds of different ways. So heap operations are going to be inevitable. I have an example here where I've just got it using a set. The fact that a set just has a unique entry for each value you give it. I'm using it to count the number of unique characters in a string that I give it. The set itself is on the stack here. That's great. But it's going to reach out to the heap in order to build its own internal data structures, which is typically a tree. And that could potentially result in a large number of heap allocations, which we all know can be slow. Heap allocations sometimes lock, sometimes they result in fragmentation. You know, they're very complex algorithms, but they don't always deliver data fast. Also, they're not so great for cache access because heaps tend to give you pointers from all over the place. So how can we easily make more use of stack or contiguous heap in dynamic data structures? And the focus is on the easily here. C++ standard library has always had allocators. So it's always been possible to do this. It's just been one of those situations where you end up getting those horrible long template errors, which take you ages to decode. It's never been a nice thing to do, and it's actually put a lot of people off, I think, actually really, really doing this. And some of the problems are, you know, once you start to do this, if you have two different custom allocators, a string type declared with one allocator is a different type from one declared with another type of allocator, which is annoying. And often what you just want to do is say, well, here's a container, use this allocator for everything inside you. And it can be tricky to do that. Also, you end up proliferating template arguments kind of all the way down into your functions because you're now dealing with all these custom types everywhere. Not nice. So C++ 17 STL supports an alternative approach, which actually Bloomberg, as you probably know, have been involved in developing, polymorphic memory resources. So this is a custom allocator that can be specified at runtime without it being part of the type. So strings are just strings, vectors are just vectors, maps are just maps, regardless of allocator. The allocator is automatically propagated to nodes and internal objects in these implementations of the containers that support the polymorphic allocator, which is neat. And you don't have to worry about this template proliferation all the time. So how does this work? The C++ 17 STL defines this interface for a new kind of allocator, which you can very easily build your own allocators from. And all you really have to do is override, do deallocate, and do is equal. Do is equal is just allow you to say, well, if you use my allocator for allocating some data, you can use this other allocator to free it. It's a helpful thing. I've never actually needed that, but it's in the standard. And for backward compatibility, there is a thing called polymorphic allocator, which is the thin wrapper around a pointer to PMR memory resource for backward compatibility with the old standards. So you can actually plug this into the old containers if you need to. Visual Studio, if you're using Windows, have this in production from 2017 onwards. And my understanding is libc has it still in experimental. That information may be a little bit out of date now. I'm primarily working on the Windows platform. So let's see how this thing actually works, and also how easy it is to use, because I think that is maybe the more important point that I'd like to make. So here we are. Here's my little example code. It's going to take this roughly 80-character string and find out how many unique characters are in this. So before we do that, we kind of need to be able to understand the behavior and observe it. So I'd like to be able to write a custom allocator that just counts for me. Hopefully this will one day be in the standard. I'd like to write a custom allocator, plug it into my set at runtime, because that's easy now, and then just see what happens. So how do I write that allocator? This is basically it. I just have to override do allocate and do deallocate. And all I'm doing is keeping track of how much I've currently got allocated, how many allocations I've done, and what the maximum size I ever hit was. So my do allocate and do deallocate functions. So the actual allocations are just going to be whatever's passing by the parent, which by default is going to be the default allocator, which eventually calls malloc and free. So who wants to guess how many times we're going to call malloc when I run this for this roughly 80-character string? Hand in there. One time. Any other? One. Okay. This is true. This is run with full optimization, release mode build, 86 allocations. Surprising, right? Wow. But then you think about what's going on. You know, every time I pass a string character in, as we iterate round, if it's a unique character, I'm having to add a new node within this tree inside the set. And if the set's not being particularly smart, it's going to just call malloc to make space for that node each time round, plus some extra housekeeping, minus the times when we actually duplicate characters. But yeah, surprising, right? So nice, neat code, but not the best in terms of performance. In this case, 13.3 microseconds. So introducing the monotonic buffer resource, which people might know as a sequential allocator. There's all kinds of other words for this. An allocator that, when you allocate, it just advances a pointer along a buffer that you give it. When you deallocate, it does absolutely nothing. So in this case, when I allocate 24 bytes, I get A. Allocate another 32, I get B. When I delete A, I completely do nothing. When I ask for C, 8 characters, I get it from here, as if A was still in use. Very, very fast. Can use lots of memory, but very, very fast. I can just plug this in and to see what happens. So if I plug this in, very easy to cascade. So I've now got my counting memory resource, which is the thing that really calls malloc and free, is going to be plugged into my monotonic buffer resource. So when it needs memory, it gets it from my counting allocator, which gets it from the system. And I'm going to pass that to the set, see what happens. So hurrah, we've done better. 8 allocations, 4.5 times faster already. The reason for this is that the monotonic buffer resource itself will grab data in chunks. It doesn't actually, it basically says, well, I'm going to have a reasonable size of buffer that I'm going to get, I'm then going to use, maybe I need to extend eventually. And it would end up extending 8 times in this, or 7 more times in this case. So this is a great improvement. We're still eventually going to the heap 8 times, but it's a great improvement. Can we do even better? Well, based on the kind of work we know we're going to be doing, let's actually give it a bit of a hint. And so, well, actually, when you first start up monotonic buffer resource, why not grab 4K of data? Just as a little favor. We're just giving you a favor. So now what happens? We run this. 1 allocation. It goes for that 4K. That's all it needs. So we've shaved off a little bit more time now. Do you think we can do even better? Any suggestions? At the back there. Align it. I think it's probably going to be aligned anyway, actually. I know Victor knows the answer. I'll go behind you. Right, great. So if we use the stack, you think trivial change, right? Is this going to make much difference? Let's run it. 0 allocations, because the monotonic buffer resource has no idea where that data's come from. If you give it a size, it'll allocate some. If you give it a buffer, it'll just use it. So we give it a buffer, tell it how big that buffer is. It will extend if it needs to, but in this particular, and hopefully the common use case, it literally uses the stack. Allocating on the stack is really fast. It's literally move the stack pointer. This is local to the thread, so there's no need for any thread local storage or locking or anything like that. This is literally the stack. So if you know your code is doing, something like a monotonic buffer resource is really, really helpful. You can get it wrong. You can easily end up looping with one of these things, and you end up using huge amounts of memory. But if you really understand what your algorithms are doing, and then this can really help. But the point I'm really trying to make here is not so much monotonic buffer resource, which is a great tool, but the fact it's so easy. It's so easy to plug these allocators in. Question, just there. The monotonic buffer resource itself will extend. So if you, yeah, it will go to heap. It will go to its parent allocator. So you could cascade things. In fact, example here is actually these are the pre-canned allocators you get. The null one is interesting, which is great for tests. If you want to prove that your code is not making any real heap allocations, plug in a null memory resource, and it will assert if you try and do any. But there are also pools, which can be thread safe or not. Here I'm actually building a heap, effectively a pool on the stack. So here's my monotonic buffer resource using the stack. And then I'm actually cascading an unsynchronized pool, because it doesn't need any thread safety, for data within this thread on top of that. So it's kind of a stack-based pool, requiring no locks, but probably lots of memory. So interesting. So try it. I think it's a real refreshing update to what we've had for a long time. So I'm now going to quickly talk about how we make data layer algorithms themselves run a little bit faster using a few techniques. So imagine a worksheet, and we're going to be currently displaying these 3 rows on the screen. So as these rows update, obviously we're going to have to do any calculation and formatting and get them on the screen. If the scroll position changes, we're going to only throw the rows we need to the display. The concept of virtual grids is known pretty well. That's how many UI systems work. However, what happens if we sort the change column over here? We only need these 3 security and price rows, but knowing which 3 rows we need depends on us evaluating the entire sorted column. So we have this concept not only of windowing rows, but actually having non-view portable columns. So there's a minimum set of the columns that you need to fully evaluate in order to decide what should be on the screen. So this kind of collection of, we call them windows, within the data allow us to still do minimum amounts of work to update the screen. Obviously, in a small example like this, it doesn't make much difference, but once you've got huge numbers of columns and large numbers of rows, it really, really helps. Something else that we do is we try and not do work within worksheet expressions as much as possible. So, and you find that actually the kind of expressions people put in these worksheets, particularly application teams, they're not just, like this one, ask minus bid, for example. Maybe it should be ask minus bid, that's right. They can be machine-generated, expressions with tens of thousands of characters in them sometimes. We've been quite surprised how enterprising some of our application teams can be. So what we like to do is actually just mark cells dirty until they're actually required. So when these 2 cells update in the bid column, we mark their dependencies dirty, but we don't actually evaluate them until we really need them. So at some point, the UI is going to be told there's an update. It's going to come back and say that the rows and columns it needs, and in this case, it's only going to calculate the top one, because it doesn't actually need the next one. So we have a system where we try and minimize the amount of work we do all the time. Another thing we do is update coalescing. So you can imagine if this is a trading blotter, not only a price is going to be changing, but new orders are going to be coming in all the time, resulting in row inserts and deletes, and moving things around and so on. So here we've got maybe an important order coming to the top. We're going to insert a new one that's coming in. We're going to update the values in that one. We're going to now delete a row because it's become stale, maybe. And this is going to obviously be a lot more complicated. This is a very simple example. But there are going to be this continuous stream of operations going on. If we choose to sort of package some of them together, we can actually do more efficient operations. And in this particular case, we could just, the result of those 4 operations can be more simply done by just deleting one row, inserting a new row, and updating it. And So we've actually, in this case, just reduced the number of operations by 1. In reality, it can be, a large percentage of operations can be coalesced and reduced. Doing okay so far? Everybody still here? Embedding Chromium, we're going to talk about just for a moment. Going back to the picture of the application container process, what's actually going on in here. So we have these sort of fundamental pieces. As I said, we used to have a sort of homegrown C++ UI that was very fast and efficient, but it needed programmers to change anything in it. And you could kind of tell that the UI was built by programmers. It wasn't the prettiest thing in the world. It didn't have any of the attention to detail that the graphics designers and proper UX experts can bring to things. Embedding Chromium brings us the full richness of HTML5, CSS3, and JavaScript. So graphic designers can now use tools, standard tools, to actually build pieces of the UI, even though this isn't actually a web app. And it's not just look and feel, but actually behaviors, so nice rollover effects and so on, and animations and all these kind of things if they're needed. We get a few things for free as well. The renderer itself, built into Chromium, supports hardware acceleration, GPU acceleration, which is a nice thing not to have to implement yourself. Things like accessibility integration. There are platforms within Windows, in our case, to allow third-party tools that are there, for example, for people who have sight difficulties, to read out the text in the UI in a way that allows them to navigate and even trade. And by embedding Chromium and using that UI layer, we get a lot of that for free, which again is a really, really nice thing to have to do. It's amazing seeing somebody actually trading with the screen switched off. Absolutely wonderful to see that people that would typically have real challenges can use our system in that sort of way. JavaScript is required to update the DOM. We tried when we were first experimenting, directly going in C++ straight into Chromium, which kind of works, but you end up with an inconsistent view of the UI world from your JavaScript, and it just got us into a big mess. So we settled on a design where really you have to go via JavaScript to get to the DOM, and you might think, oh, that's going to be really slow, but actually, I as a C++ programmer, I'm continually surprised how fast modern JavaScript can run in one of these modern engines. It's pretty impressive. The jitters in there sometimes often do surprisingly well, and it's because they have a lot more context than maybe a compiler for C++ might have at compile time. They can really understand what's really hot code right now and optimize incredibly well for that. So yeah, the world has been changing. It's really interesting. So this is kind of how the whole thing fits together. We still have our native C++ layer, but some bindings that allow us to efficiently plug in to JavaScript. We also have some extra services that allow us to do screen management, to access, in a protected way, some system resources that we do want to expose into the JavaScript world. And we actually have various kind of protection levels to allow us to control actually what is allowed to be used. Plus the fact that the embedding engine itself supports proper sandboxing onto the OS. So what are some of the challenges to make this work really, really well? As I said, we kind of have to use the DOM to update JavaScript. To write efficient JavaScript, we actually use tools to help us a lot. We have built into our CI and deployment systems, pipelines that actually do a lot of pre-optimizing of JavaScript using industry standard tooling, module inlining, minification, dead code elimination, and so on. Get rid of all the comments. You don't need you to keep remembering that this stuff is actually going to be interpreted when it first hits the desktop system. And introducing discipline to JavaScript really helps when building a JavaScript infrastructure layer. Something that we actually sponsored with the ECMA standard committee is private class fields in JavaScript. So having the concept of private data in your outer APIs that well, actually anywhere within JavaScript, but so that people can't abuse the APIs that you give them. quite a contentious subject. Some JavaScript developers want to do anything in JavaScript, but actually having this support in the language is really, really helping us. And also we are migrating to TypeScript, which just brings in a kind of an infrastructure-style discipline to writing script-style code. And now that can leverage these natively supported private class fields. And that's something that we're actually contributing back to the groups that build and maintain the tools. As I say, JavaScript is actually pretty fast. So often the focus needs to be on efficient marshalling to and from JavaScript. So we've spent a lot of time making things like our Datum data type marshal very efficiently across that boundary. Minimizing GC. Welcome to GC for anybody who's only done C++. It's a whole interesting new world. GC algorithms nowadays are actually garbage collection, by the way, for anybody who doesn't know that terminology, has really evolved over the years. Very sophisticated now. JavaScript engines will do a lot of the scanning phase actually in background threads, but at some point we'll need to synchronize with the main thread doing the JavaScript work. And you really want to be careful, particularly if this is the UI thread, to not have a stutteriness on the screen just because GC is happening. So really the objective is to minimize GC. And it doesn't always just happen when your JavaScript heap is full and it needs to actually free space. These engines tend to want to do GC anytime they feel, oh, there's some cleanup to be done because I've got a lot of temporary objects. And we can find that even inefficient code that kind of goes in and out of the hot path and gets jitted and deopted and back and forth results in extra GC because objects containing code are being continually created and destroyed. So it's something you have to be really, really watchful of. And often, the sign of an efficient running system is when GC is low, even if you're not using that much memory. So it's a very interesting measurement. Lifecycle. Obviously, with GC, you've got non-deterministic lifecycle of objects. If you're writing pure JavaScript, the engine handles it really, really well. However, we've got this hybrid model where many of our JavaScript objects are going to be managing native C++ objects. And of course, lifecycle has to be preserved across that boundary for things to work. So what we find is that native C++ objects can end up living much longer than we might expect them to. So here's my application. I'm going to run it through once, produce some stuff on the screen. Maybe I'm going to have a JavaScript proxy object that is backing my native C++ data layer pipeline, for example. Now I'm going to click on a button, and because I'm running maybe a React-style model where changing a little piece of data rebuilds a whole chunk of the object tree that I'm going to be rendering. So we get a new object created, backing another native data layer pipeline, which might be quite big. We're at the mercy of the GC engine now. The old object, which we no longer need, may still exist. There's no reason, there's no guarantee that the JavaScript engine is going to destroy that first object. So we may end up using much more memory on the native side than we want to, ideally. So what can we do about that? Something we actually borrowed from C# is the dispose pattern, where you can introduce deterministic lifecycle of expensive components, even in a GC environment. So what I would do is actually write in my code in JavaScript at the point where I know I'm finished with an object, even though it may still exist for longer, call dispose, which we can proxy through to actually releasing the final reference onto our underlying C++ object and actually more deterministically control the lifecycle of things happening down at this level. Some purists say, you shouldn't need that level of detail. We're engineers. Sometimes you have to make these compromises and move away from the sort of the purist approach. We've actually talked to the teams at Google about, is there more can we give a hint to an object that it's expensive? Although it's a cheap JavaScript object, it backs something expensive. But generally, the solutions we've come up with have not really been general enough to actually fit into the engine. So this is the sort of current approach we take, which, to be honest, works pretty well for us. So instrumentation. How are we doing for time? A little bit left. Getting towards the end. It's really important for us to understand what's actually going on within this system. And there are very obvious things we can measure. We can measure CPU load. We can measure memory utilization. The slightly harder things to understand or measure are things like headroom, particularly user responsiveness. How does this system actually feel to an end user? And these are some of the things we do. So CPU load. Pretty obvious. We can ask the OS how busy a process is, how busy a thread is. We also have this concept of busyness, which is really using elapsed time measurements, how long we spend doing certain types of activity during a sample period. How long do we spend actually in the Chromium renderer? How long do we spend processing incoming data? How long do we spend updating a worksheet calculation? And together, these really give us a good indication of where the system is spending its time, even when you can't afford to run a profiler, a full profiler, and also give us a good indication of spare capacity. It also tells us things like, high busyness using elapsed time, but low load indicates waits or even time slicing. We might be running on a VM, which is, there may be a VM that's supplying, 8 users, but maybe it's only got 4 cores. So something's got to give there, and we can actually measure these kind of things. And these are the sort of tools I would use to look at my own terminal to understand how it's behaving. The white line is overall CPU load on my PC. You can see why I ran a compile of the software. This is the Bloomberg app, bubbling away at the bottom, and this is telling me a breakdown of my different layers in my Bloomberg system. So this is the kind of core manager process in gray. This blue thing is instant Bloomberg. It's our instant messaging chat system, which we originally built for our own use, showed it to clients, they loved it, and we now see clients with 300 or 400 chat rooms open at a time actually trading through the chat room. It's because it's considered so reliable. There's this community of 300,000 people that can instantly chat to each other within this secure environment, and everything's compliant, everything's logged, so it's a very well-respected system. So another view, which is kind of interesting, is a 3D view. I asked the team to build this, and they said, why do you want 3D? It's just purely gratuitous, right? Never going to be useful. But actually, I find it is useful. The green here is our main process. The light blue is my instant messaging process. There's a few other background things churning away for a while. And then I can see these other little things that pop up occasionally, which are little, in some cases, sort of management tasks that are maybe making sure that my JavaScript is up to date. There's been no, emergency fix release, or other kind of things that wake up, which maybe I would never really notice in a 2D view. And equally, we can look at memory. Memory is really critical for us, not only overall memory usage on the machine, but per process. We tend to run 32-bit processes. People think, why? Why? Partly is because of the size of these grid cell objects. If we move to a 64-bit platform, suddenly pointers get a lot bigger. And so if these objects like the datums are having to now sometimes hold pointers to long strings, suddenly the thing has got a lot bigger, which may not be an issue. We can't control how much RAM our clients have on their desktops, so we have to be quite conservative. We'd love to go 64-bit throughout, and I really hope we'll get that opportunity. We might have to make some tricks, like maybe assuming that we don't use the full 8-byte address space in pointers, which I'm not sure I want to do that. That might be even more extreme than reusing the unused bits of a double. But we'll see what happens there. But yeah, so we tend to be 32-bit, which means we have a limited address space for each process. I call this the cake view. So you can kind of see how memory usage grows, and you think, something must be leaking here. But actually, over the day, I'm going to be caching more and more data. So this may actually be normal. Gray is our management layer. Blue is our instant messaging system. The blue and the yellow, the orange and the yellow ones are actually, I started running these metrics viewers and then gradually loaded those up with data. So again, we can get a really good understanding of how our system on the desktop is behaving as a whole. When we want to drill down into where memory usage is, the talk I gave last year, which is actually on YouTube, is how we can do live profiling of memory usage within a process. And we end up getting these histograms and trees that actually show you the call stacks that actually use them, make the most memory allocations. So if you're interested in that kind of thing, please have a look at the talk there. User responsiveness. So how do we measure this concept of slowness? And actually, something that we've really settled on is that what's the thing you first do when you're trying to see how responsive your network is? You run ping, right? So actually, pinging the UI thread is a really good way of understanding how ready the UI thread is to do new work. And we use that a lot because if the UI thread is busy doing something else, then it can't respond to a key press or a mouse click or a mouse move or a mouse hover or any of these kind of things. So actually, having the UI thread ready to do new work as often as possible is a really good way of ensuring a good user experience. Obviously, there's other factors, how long it takes to do a network request and so on, how long it takes your service to respond. But what users are really looking for is they want something to happen as soon as they interact with the system. Even if it's not the full thing they're looking for, it just has to feel responsive. And so, how do we measure these kind of things, and how do we really understand what's going on that might slow down the threads that matter, such as the UI thread? It's kind of what I just said there, actually. So here's a very quick example. This is our instant message system, and I'm typing here, and it feels jerky. So why is that? How can I actually analyze that? The thing that you saw at like I said, one of the things we can do is we can look at the JavaScript level. So because we're embedding Chromium, we can actually use the Chrome DevTools Inspector to see what's going on in the JavaScript world. So this is very good for sort of nice, quiet analysis in your own time when you have no distractions and you can really understand what's going on at that level. But it doesn't really help us at the native level. So we have this tool built into the terminal, which allows us to see things like what kind of work is going on here. Chromium work towards the top. The yellow is Chromium work. The blue is data layer work. Down here, we're measuring the yellow triangles are actually basically this ping time to the UI thread. And you can see where the keyboard was stuttering, it's because this is 1 second, actually, the scale here for each of these little charts. You can see that there were significant delays in the UI thread. The red are actually timer latency. So I fired some timers, or queued some timers, but they fired late. Because on Windows, timers are the lowest priority thing. They only fire when there's no other work to do. So seeing how late timers are is also a great indication of whether we're too busy. So this can show us, the points where we're actually causing the UI to feel bad for users and really drill down there. How do we actually do timing in the UI thread? This is just a nice trick, which I thought I'd just quickly show you while we've got a few minutes. So this is a very typical way of timing some work. RAII principles, you have a little scoped guard that when it's constructed starts timing something. When it goes out of scope, it stops timing. And you do some work within that. Maybe I have different kinds of work in some enumeration that I'm going to want to measure. What does the implementation look like? I've probably got a little stack, although it probably wouldn't be built using a stack because that's actually a deck inside. Maybe some handcrafted little thing. And I'm going to just have a vector of timers which start timing and stop timing so I can measure different kinds of work. What does one of these timers actually look like? This is actually something that I just think is a really neat trick done by one of the members of my team in London. So this is a timer that can be called from one thread but observed from another thread. So I can have the UI thread running, and separately I can come in and say, how busy are you right now? Whether you're currently doing some work or not. So we have this simple data structure which just has a level which protects against recursion. So I can actually start timing the same kind of work recursively and stop it but only measure at the outer level. But also, I have this interesting way of actually subtracting time now from my tracked time when I start timing and adding it when I come back. It seems a little bit odd. But if you see how this works from my observer side, so imagine this is running in another thread that I'm using to observe what's going on. This is just a really neat way of, in one atomic variable, tracking how much time I'm using, but also whether I'm currently timing. Because if I come in and I'm actually currently timing something, all I've stored is the time that work started. So I need to add in my current time now in order to say, well, I'm still doing that kind of work. So the amount I've done so far includes the time now. However, if I've done some work but finished, the value is going to be positive. So I can just return it directly. And this is just maybe this is obvious to everybody. I found it really clever, actually, just to be able to have this notion of how much work I'm doing plus whether I'm doing work so neatly held in a single atomic variable. So we actually use this ourselves in this kind of system where we have the main thread timing things, saying what it's doing in a very lightweight way. We have a monitor thread which basically writes this data into circular buffers. And then we have a separate UI thread running this thing, which allows us to observe what's going on. And it's relatively unusual to have multiple UI threads in the same process on Windows. So, but this really works very well for us. Something that we do in the last few minutes is we actually allow this system to be recorded. And it relies on the fact that the way we create data is to create objects from our servers is to avoid round trips. So rather than saying create object and give me a handle, we typically say, give me let's find a free handle without any kind of round trips, and let's use that handle to create an object and then send data to that handle. So it's purely push. So the nice thing about this scheme is that not only does it result in no round trips on the application, between the application and our clients, but it's recordable and replayable. And we use that for example, here's a bunch of interactions running. We can be in recording mode. We're not actually recording what the user does, but we're recording the result that comes from our servers to those particular user interactions in such a way as now I can run in a slightly different environment here, which is running a different executable, but embedding the same Chromium, the same data layer, and so on, and actually replay at different speeds in different versions of software. So actually, this kind of gives us a lot of free integration testing. Because we can just record all these things that are going on and replay them through profilers, through our test systems, to really understand how our systems are behaving in these different scenarios. Last piece in my last 3 minutes. WebAssembly. Who's heard of WebAssembly? Most people, probably. Who's used WebAssembly? Few. Alex is in my team. Of course he's used it. WebAssembly is interesting. I actually heard about WebAssembly first, really, this time last year, as I said, when Adi was talking about it. And when Bjarne Strastrup was here doing the keynote last year, I just happened to bump into him in the bar, which is a real privilege. And I asked him about WebAssembly, expecting him to kind of poo-poo the idea, and said, oh, no, new platform for C++, fantastic, really, really interested. So you heard it here first. It was this conference. That he said that. It's just been a really intriguing journey. We've actually started to really look into this. How can we bring C++, mature, complex C++ into the browser environment? And I just wanted to touch on a couple of things that we've been doing. So what is WebAssembly? It's a binary instruction format for a stack-based virtual machine. It's very fast, it's very compact, it's close to machine code, and it's pre-optimized. Secure, runs in the same sandbox as JavaScript, and it's standard. It is currently supported by all the major browsers. It's portable, and you can actually you can actually bring in code from different languages and run them in any of these browsers. So for C++, there's a tool suite called Inscriptum, which generates this thing called a WASM bundle, and for something like Rust, there is WASM pack, which generates the same bundle and bytecode system around it. In detail, the C++ toolchain looks a bit like this. It's using Clang and LLVM. So this is credible, powerful, industry standard toolchain. There's nothing throwaway and sort of prototype about this. This is real. And the end result through this is something that can actually be hosted directly in the JavaScript engine. And it brings in, actually, if you need it, there's a whole sort of POSIX runtime to allow you to use this kind of in the confines of the sandbox, obviously. How do we hook up to it? This is our normal production desktop system. The experiments we've been doing involve actually taking the entire data layer pipeline, running it through this tool set, and producing a WASM version of this, directly running inside the JavaScript engine. And we get some benefits. Dynamic download, obviously. Efficient binding, the actual binding layer. We've done some benchmarks, as you'll see. And it kind of opens up a lot of intriguing possibilities of sort of blurring the lines between what should be in JavaScript, what should be in C++. We're thinking, there's everything from calculations to maybe taking pieces of our UI layer that do some complex transformations on for the DOM. Maybe they belong in this world. Maybe charting packages, the calculations for those belong in this layer. How you actually hook this up together from your C++ is you have to make use of some macros currently. The guys here in my team who are kind of dotted around have been actually using a lot of modern C++ variadic templates, index sequences on tuples and so on to actually automate this whole process. I don't understand this stuff. I had a slide on it, but I thought I'm too scared to talk about it. So find the Bloomberg guys if you want to understand how this works. But it's allowed us to build a generic binding layer that can target WebAssembly bindings, V8 JavaScript bindings, Python bindings, and so on for our C++. And we're actually contributing this back to the Inscription folks so they can actually make this more generally available. Performance is very interesting. What we found is, worst case is where we're doing heavy C++ computation work, but only 40% slower than native C++ running on the same hardware. So it's within the order of magnitude. So it's not ultimate performance, but it's close enough for many scenarios, which I find really intriguing. The best case is actually where we're doing a lot of marshalling across the boundary. We've actually found that the boundary between JavaScript and WASM is actually more efficient than our current boundary between native C++ and JavaScript. So it's very, very practical. This is a very intriguing sort of world we're living in now. What's quite nice is that something we actually sponsored on the JavaScript world was a new data type called BigInt to allow us to have long-length integers in JavaScript. Particularly financial people, have sometimes very large numbers they're dealing with for profit and loss, and they want full precision on these integers. JavaScript used to not support that till BigInt. Last week, I noticed a tweet from one of the WebAssembly team. This guy is actually using that to actually implement marshalling of i64s for WebAssembly. So it's quite nice that these worlds are sort of colliding here. A bunch of references. A couple of our WebAssembly folks are on Twitter. If you follow them and see who they are too, you'll get in with the whole WebAssembly ecosystem. There's some really interesting work going on there. So, in conclusion, a couple of minutes over. Sorry about that. I know it's lunchtime. It's possible to leverage modern open source software in conjunction with specialized custom components to build a high-performance, reliable desktop front end for certainly what our clients consider is a mission-critical data service. C++ and JavaScript can be made to play very nicely together, but in order to do that, and in order to make efficient C++ systems for the desktop, you do need to pay attention to detail. Something that C++ is obviously great for helping us do. And you just have to have a real understanding of your system behavior, and how do you do that? You add in comprehensive metrics. And as I say, WebAssembly hints at a very intriguing future. Maybe our system will run in a browser one day, and won't actually need a lot of this custom sort of stuff around that. But interesting times. Thank you so much for coming along. I hope that was mildly interesting for all of you. I'm happy to answer any questions, but please go and have lunch. Thank you.